Adam Boston. This is my first lab for Introduction to Physics at Georgia Tech. So the purpose of this lab was to track the motion of an object at constant velocity, as well as code and model an object at constant velocity based on observed data. And the main physics principles at play were Newton's first law and the position update formula. And a brief description of our results found that the observed displacement was less or at a lower magnitude. It was because it was in the negative direction, but the model had a more negative, or magnitude was larger. Essentially, it maintained its velocity due to some assumptions we made. So to elaborate these main physics ideas, Newton's first law explains that an object in motion will stay in motion unless a force acts upon it, or if it's at rest, it will stay at rest. So if the object we're having is going to be at constant velocity, then the net force is going to assume to be zero, which is hard to replicate in real life, but those were the assumptions made for the experiment. And additionally, the position update formula was important. This was the formula behind the data in the first place. It found that the change in position or displacement was equal to average velocity times time, and the average velocity is the same as the initial and final velocity because it's assumed that the velocity is constant. And it was also assumed that net force is zero, which is not the case, but I will get to that. But of course, the purpose of using these pieces of data is because, one, if it's going to be constant velocity, then it has to be at the net force has to be zero. And if it's the change in displacement is based on that average velocity times time, of course. Now, for the experiment itself, we had a system of a wood cylinder, and the surroundings was the Earth. And the initial conditions of this wood cylinder, it was 1.5 centimeters in diameter. That's about it. For the first frame of the tracker data, the origin was centered around the first frame, with positive x being to the right direction. Our cylinder moved to the left, meaning its displacement was negative, which would be seen in the results. The cylinder was allowed to roll from a height to gain some initial velocity, and the first frame was after it had landed on the table to give it some initial velocity. Which was in theory supposed to be constant. For the code, the initial velocity vector was calculated based on the two frames of the observed model, which means we found the displacement of the first two frames and then found the change in time, and that was the initial velocity vector. And since velocity is constant, it was going to maintain that throughout the code. The net force was also set to zero, and of course this initial velocity vector was in the negative direction. As the results show, the predicted or the computed data shows of a larger magnitude of displacement than the observed, because the observed experienced a net force, which was friction. Now, between the normal force and gravity, which was a net force of zero, and since it was rotational motion based on physics, it did maintain its velocity for, towards initially compared to the predicted, but as the force deceleration began to accumulate due to the force of friction, and then the predicted data maintained its velocity, therefore it had a larger displacement over time. But they do show pretty linear relationship, and given that velocity is the derivative of displacement and displacement is linear, it could be assumed that velocity is constant for the most part. So what if the axes were flipped? Well, if the axes were flipped, the magnitude of the speed is going to be the same, because it is going to be the same distance traveled over the same time. The only difference is it's a vector, so it would have been in the positive direction if the axes were flipped. Our object would have been displaced the same magnitude but in a positive direction, and the data, computed data, would still have a larger displacement, larger net speed, larger net displacement. And so what does that mean? So can we ever know what the true forces are acting on at the object? Well, based on the system of surroundings, you can assume that the gravitational forces of other planets, which is technically always acting on the objects, is not present. But it cannot be assumed that there's a net force to be zero, and it is hard to get an object whatsoever to move at a constant velocity on Earth, because there's always some form of air resistance, friction. There's always a net force. And so our computational model can show us in theory what would happen, but it is almost impossible to get a constant velocity on Earth, which explains the discrepancy. And that is also a possible error, is due to the force of friction. But essentially, constant velocity can be mimicked, but it can never be fully achieved based on conditions here on Earth. And that is my presentation. Thank you.